Hi class, welcome to the next video. We're on to chapter 8.3. This is volumes by cylindrical shells. So this is very similar to the previous section, chapter 8.2. But if you remember, there were certain instances where finding the volume of a solid could be very difficult. Um, Especially when we're doing things like rotating around a point. In fact, there are some problems where the method that we used in the last section, 8.2, is it's impossible to find the volume. Okay. So we're going to move on to another method called cylindrical shells. This is typically easier than the previous method. The previous method in 8.2 is generally called the washer method because as you saw in the last example from 8.2, we have rings that are made, which is the same thing as a washer. If our solid does not is not rotated around a uh, a line, it's very possible that it's a complete solid, which I guess we could still call a washer. It just doesn't have a hole in it, right? So we kind of have a comparison between the two methods. One method we'll call cylindrical shells. The other one we call the washer method, is what it's typically referred to. So 8.2, you think of as the washer method. 8.3, we are using what is called cylindrical shells. So let's look at another method, right, for solving volumes due to rotation from the XY plane. So again, this can cover more difficult problems, like when there's no explicit form for a function. So before we saw when we try to, we had a function in X, and when we try to solve for Y, we couldn't find a singular function. We had to have two functions, right? So like if X equals Y squared, we need to have square root of X and negative square root of X to have the same function. If you remember from the previous examples, we went to Desmos and we kind of showed an example of that, right? So for these, it's much easier to compute problems like that. So we'll give an example of something that would be very difficult to do. So let's start off with the previous example that we had from the last section, the very last problem in the last section. We had the y equals x cubed, the cubit. It was bound by the x-axis and x equals 1, the point of intersection that we needed, and the line x equals 2, which was the line of symmetry for the rotation. So we're not going to go through the whole problem. We will do this problem again, but not right now. But this was fairly difficult to set up, right? Especially when we're trying to find the formula for the radius here, especially when we're finding the outer radius. I think that that is not very intuitive for students or anybody really who is doing this for the first time or the first time in a long time. It's hard to think of that. You wouldn't think of it as it's 2 minus and then, this outside function. So we're rotating our function along a line that's parallel to the x-axis, right? So I'm sorry, to the y-axis. I should change that before I put it into a document for you guys. Um, but it's parallel to the y-axis, right? And that's our rotation, right? We're rotating this way. So we need to find a function x in terms of y, right? So our disk or our washer area is variable length from the left to the right, but not up and down. Okay. So if we look up and down, it's not necessarily a variable length. Um, Height, but left to right, it does vary. The washer does vary from left to right. Okay, so this washer is a variable from length to right, but not up and down. So it's pretty easy to do this. We did it previously. We just solved for x, right? So we just basically took the inverse of this. Well, what happens if we have a different function, something like x squared plus 1 over 100x? So I specifically chose this function because it's very close to the function that we're already doing, that we've already solved, right? So is it impossible to then find an explicit function for x in terms of y? It is indeed, because we would need two functions in order to mimic this same function, right? So in turn, it makes our integration using the washer method almost impossible. if our function looks like this, even though the two graphs, right, um, y equals x cubed and this quadratic are almost identical over our interval from 0 to 1. Okay, so this blue line is x cubed. That's what the graph looks like. If we look at y equals x squared plus 1 over 100x, it's almost the same. Obviously, there's a little bit more of a dip in the y equals x cubed. But if I took this function, y equals x squared plus 1 over 100x, and I rotated it over the line of symmetry, x equals 2, it would be impossible for me to find the volume of that solid using the washer method, using the method we used in the last section. Okay, and you wouldn't think so because the functions are almost identical, right? In in area, right? Like obviously there's an area here, but how come I could do it for x cubed but not for this one? And the reason is because I don't have an explicit function when I try to go left to right to find my washer outer radius. Okay, so let's go ahead and begin with the general derivation of the method we're going to use, and then we'll return to our two examples and we'll apply that method to those examples. Okay, so let's say that we have a solid that we're going to model by rotating um, about a line or an axis, right? Very similar to the last example. Okay, we end up with some sort of a washer like this, or I'm sorry, a solid with a hole in it. Okay, so here my function f of x is, this could be a cubic, a quadratic, it could be anything, right? I have no idea because I don't have it explicitly stated to me. But let's say that I take the area under it and then I rotate it. Okay, very similar to what we did in the last example. So previously, if we wanted to find the volume for this solid, we first would cut ourselves a washer, in this case parallel to the x-axis. Okay, we take a slice of the solid, and then we would find the area of that washer, and then we would integrate that function that we got from the bottom to the top of my solid. Okay, so we would get a washer, we would find the area, we take the outer area and subtract the inner area that has a hole. Okay, but for this, we kind of run into some issues when we do that, right? Down here, we have no problems at all. Okay, so from y equals 0 until we reach the bottom of our function, the size of the washer doesn't change. So from here, the axis, to the bottom point, the whole thing looks the same. It's basically a constant function at that time. It would be very, very easy to find that. But once I go past that point, I start to run into some issues, right? So we wouldn't even need an integral in order to find that. We could just use geometry and our knowledge of cylinders, basically, right? Once we hit the function, there's two problems. The first is that our function is not one-to-one, so we're not going to find an explicit function of x, meaning it doesn't pass the horizontal line test, right? We're not going to find x equals something. We'd have to have multiple functions, right? Second problem is that the slice isn't a washer anymore. Okay, it is for a little bit, but not the whole thing. So, example, if we took it right here in the middle, I would actually have two washers. And as I move through this section, this interval where I hit two different sort of portions of my function, I'm going to have two washers with various uh, lengths, basically. So I'm going to have a couple of integrals in order to find it. So I'd have to have one integral to get me to the bottom of the function. I would have to get another function or two functions for integrals to get me to uh, this top of this inside portion, and then I'd have to have another integral for that point to the top, right? So that's very, very messy. That could take a very long time. So what we would do instead is we use cylindrical shells, right? Because this can be a real pain in the butt. So instead, consider making a small rectangle that's up and down like we normally do. Um, it's centered at some x within our domain, which we'll call x sub I. say it has a width of delta x, just like a regular triangle when we do a regular integral as normal. And we're going to, again, do the standard integration. So this is my curve of f from a to b. I'm going to find the function height at xi, and then I'll have a small width here of delta x for the rectangle that I'm forming for me to form my integral. Okay. So now what we're going to do is we're going to look at this square, at this rectangle that we formed for the Riemann sum, and think about what happens to it when we rotate our function to get this solid that we're trying to form. So as our function rotates, again, this little sub-rectangle is going to rotate as well. Okay. And it'll give us a sub-cylinder, right? The width of that cylinder will be delta x. Remember that it gets infinitesimally small, and it has the height of our function value. So we're going to calculate the volume then by looking at that single cylinder, right? The shell of a cylinder that gets created by rotating my function, and the rectangle for a Riemann sum that goes with it. Okay. So here I'm going to have an inner radius and an outer radius, and it's going to have a height of h. Right. So just thinking about what's going on here, the height in this case would be my function. This x sub I would be the value right in the middle of this width of my cylinder, and the inner radius and the outer radius would have a length of delta x. Okay. So in order to find the volume of a cylinder, it's the volume of the outer cylinder minus the volume of the inner cylinder. If you don't remember how to find the volume of a cylinder, all you're basically doing is you're taking the area of the face of the bottom, and then you multiply that times the height, right? Very similar to thinking about it as an integral. So volume is pi r squared, right? The base, the radius of the base, or the area of the base, pi r squared, times the height. In our case, the big cylinder has a radius of r2. The inner cylinder that we should be subtracting from the whole has a radius of r1. Okay? So very, very straightforward. We'll do a little bit math on this. You can pull out pi, I can pull out h, but r1 and r2 are different values. So I have r2 squared minus r1 squared. Notice that this is the form of a difference of squares, right? We can go ahead and unfactor this, right? Or yeah, I guess unfactoring would be the best term. So I'm not going to multiply it out, but I am going to sort of like break it apart to its two terms, right? It's two linear terms. So I have pi over h, r2 plus r1 times r2 minus r1, right? Now I can, well, if I multiply it out, I'll get the same thing, but this will be my volume, okay? So this is going to give me 2 pi. So you might say, where the hell is the 2 pi coming from? Okay, so if I multiply by 2, if I take 2 and I multiply it by 1/2, that turns into 1. So I'm really going to negate this 2. I'm going to do a little fancy trick here. So I'm going to have 2 pi times h times 1/2. So 1/2 and the 2 breaks me back down to just a regular pi. R2 plus R1, R2 minus R1. So remember, the width here is delta x. That's this length minus this length will give me what's left. That's the delta x. The value right in the middle here, okay, this x sub I, is going to be the average distance between R1 and R2. It's right in the middle, right? So how do we find the average? You add those two values together and you divide it in half, okay? So my integral, right, is 2 pi, my function height, the mid value, that x sub I, times delta x, the width. Okay, so that's how I find my volume. And so when I simplify this, I have my 2 pi, I have my function height, which is f of x, actually that's here. This h is f of x. X is the value that I'm at, some x sub I, and the difference, this delta x, is this R2 minus R1. So throwing it together as an integral, it's the bounds from a to b of 2 pi times x times my function um, with respect to x. This is much, much easier to do than creating the washers. Okay? So let's look at this another way. I like this breakdown a lot. It kind of plays with the values here a little bit. The derivation is nice. But we can also think about this as just unfolding a cylinder. So let's say we take the cylinder, right? It's empty in the middle. Its width here is delta x because, again, that's what I use. I use a rectangle, remember? It's a width of delta x and a height of my function value. Okay, so then the width here is delta x, height of the function value. Okay. And so delta x, the distance here is x, especially if I'm rotating about the center. And let's go back just to like, right, I'm rotating about the center. So the distance from here to here is x sub I, some value of x, wherever I'm at on my function. Okay. Function height is f of x. If I unroll this out, well, remember what the circumference of a circle is? It's 2 pi r. So 2 pi and the radius here is x. Okay. My width, if I cut this across, is delta x, and the height is f of x. So how do I find the volume of a rectangle? I multiply all the sides together. So I'm really just taking a thick cylinder and I'm unraveling it to a rectangle, and I could just use that, and I get the same exact function. I get the circumference, 2 pi x, the radius, times the function height, which is f of x, and this differential here for x is the width. So that brings us, again, to our function. And this is very, very easy to calculate. So let's go ahead and do this one more time. Our example that we ended with in the last section, chapter 8.2. So we had this crazy looking thing going on. Remember, we had to find an outer radius, we had to find the inner radius, we had to subtract them. It gave us a function. Then we integrated that from 0 to 1 because we were integrating with respect to y. Here we could do everything with respect to x. So my volume is 0 to 1, okay, because that's where my function lives. So I'm not going 0 to 1 this way. I'm going 0 to 1 here. I'm just looking at, again, only my function, only where my function starts and my function ends. So all I have to do is look at the function here. Okay, so my function starts at 0 and it ends at 1. Okay. The radius is 2 minus x. Again, that's because I'm starting at 2. So whenever I'm looking at the radius that I'm doing here, right, the circumference from the spin is going to be a full value of 2 minus whatever x I'm at, right? So if I'm at this x, it's a full 2, and then minus that little value. Oops. And times x3, which is the height of my function. So I can pull out the constant. I can multiply this x cubed across. This is very easy to integrate, right? Polynomials are one of the easiest things to integrate. So the x to the 4, just 2 times 2 is 4. So the 1 over 4 cancels the two 2's. I'm going from 0 to 1. This will be 1/5 pi. Okay. Oh, I'm sorry, there's a 2 here. 2/5 pi times x to the 5. Remember, same thing. These are just x values. So when I plug in 0, it does nothing. So I really get pi minus 2 pi over 5. Okay. Or 2/5 pi, however you want to look at it. So this is 5 over 5 pi. So my answer is 3 over 5 pi. Okay. So we can go ahead and check this against the work that we had previously. Check the amount of work. This is not a lot of work. I'm not going to go back to that video. You can go back to that video or you can look at the write-up that you guys have for the previous section. And it was a lot more work than that. Okay. So when we're finding volumes by rotation, sometimes finding an area of a slice is easier than computing a cylindrical shell and vice versa, right? So what I mean by that is sometimes the washer method is easier. Sometimes taking a slice and slicing it in Y or slicing it in X and looking at that washer that's formed, that cross-sectional area, sometimes that's easier than trying to use a cylindrical shell just because of the multiplication that happens when you do it. Um, so you kind of have to pick and choose, right? If you try one and it's getting a little too crazy, switch to the other one and maybe it'll make it easier. Okay. So again, you want to use your best judgment to determine which method you think is going to be easier. Things to consider. Um, are my top and bottom boundary curves easier to use, or is left and right easier to use? If it's top and bottom, then maybe I want to use cylindrical shells, right? If it's left and right, maybe I use the washer, or vice versa, right? Depends on the direction you're rotating and what have you. Are my limits of integration easier for f of x or for g of x? Okay. And is there a way for me to use one integral or do I want to use multiple integrals, right? So you just really have to go question by question. Okay. Let's do another example. Let's use cylindrical shells to find the volume of the region bound by x equals -3y squared plus 12y minus 9. So again, this is a parabola centered on the x-axis. So it opens to the left or the right. It's negative here, so it probably opens to the left. Um, and x equals 0. Okay, so we're using the y-axis, and we're going to rotate it about the x-axis, I'm sorry. Okay. So if I wanted to graph this, I could just graph it in decimals or something to see what it looks like. Or I could try to factor this out, find the zeros, you know what I mean? Do all the stuff that I know how to do with parabolas in order to figure out what this looks like. So here, it's got zeros at 1 and 3. Um, line of symmetry is at 2, so I could have probably fairly easy, just pulled out the common factor of 3, and then factor the quadratic in order to find the information I needed. Okay. So I'm going to take the x-axis, and that's my axis of symmetry. So I'm going to rotate this around the x-axis. So when we set this up, I'm going to have 2 pi times my value of y. That's where I need to move to in order to find the radius. Right? So we have this square here that helps me to identify the direction that I need to take a slice. And so my function value is given to me, right? So again, if you're having troubles trying to visualize why I'm doing anything, just kind of tilt your head to the right and be like, oh, I move up this direction before I can find my function. So I move up to a y value and I evaluate my function to get the function height. I don't have to do any weird adding or subtracting things because I'm not shifted by 2 like in the previous example. I literally just go, my radius starts from 0, right? So here I have a radius of 1, here I have a radius of 3, so y makes sense, right? Radius 1 up to radius of 3. Function value. And so if I evaluate this, that's all I had to do. I just literally put everything into its place. I'm going evaluating from 1 to 3. I'm evaluating on the bounds of my function, not 0 to 3, right? Just 1 to 3. So I start to do the math. I can distribute y through, which is very, very easy from here. I'll take out this extra parentheses when I put the write-up in. Sorry for that. Little formatting error there. Anyways, this goes to 4, 3, and 2, and then we have the reciprocals for each value, right? So again, I have the 2 in front. So the 2 and the 4 cancels, so I got 3 and 4. Okay, I get my next one, 8 pi y cubed, and -9 pi y squared. So these are not zeros, they don't just go away, so I got to actually evaluate each part. So if we go slowly, I'm going to put 3 in here. So 3 to the 4th power is 3 squared times 3 squared, right? Or 9 times 9. So I'm going to have 81 and then minus 1. I'm only evaluating at y, so I like to just pull out the constant and then just put my function values inside of the parentheses. Here will be the same thing, 3 cubed, so this will be 8 pi times 27 minus 1, and this will be minus 9 pi times 9 minus 1. Okay. So this will be 80, 26, and this will be 8. Okay. So I just did the 8 right away. So I like to do all of my calculations at the very end. I like to pull out, factor, all those kinds of things. So here you can see there's an 8 in this term. There's an 8 in this term, right? Because 40 is 5 times 8. Here, this is 9 times 8. So if I wanted to, I could pull out 8 pi and then just have minus 15 plus 26 minus 9, which would probably be the better way. But here you see I'm actually multiplying it out. And I split this across. So again, this is just sometimes how my mind works. I'm not a calculator person. I just do it by hand. But I don't sit here and go the old-fashioned way with 26 and 8 on the bottom. And, right? I just kind of I use algebra with my arithmetic. Okay. So 340 is 12 with a 0. 26 is 20 and 6. So 8 times 2 is 16. Add a 0. 8 times 6 is 48. And then I could subtract the 72. So I should get a negative, another 48. So it looks like I combined this 72 first with the 120 and combine my negatives, right? So that's 192. Then this gives me a, what's that, 208. So 192 and 208, you find the difference. It's about 16. So pretty straightforward there. So we did, say we did the same problem that we just did through cylindrical shells right here, but with the washer method. So again, this is pretty straightforward. There's some bigger numbers, but we just did it with arithmetic. We could have just kind of went straight here and used a calculator, I guess, and just kept it in terms of pi instead of doing the mental gymnastics. But let's go ahead and do this to the washer. So if we did this to the washer, okay, obviously I would want to take a slice this way, okay? That way I get my ring, I get the outer ring and the inner ring. In order to do that, I would kind of need to see the heights here, right, from the center to here to get the outer radius and the center from here to get the inner radius, which means that I would need to have a function y equals something in x, because now I'm looking at x values, which you could already see is going to be very difficult to do, right? So, okay. So I have this, my slices then would be this way. And so when I start to rotate this around, it's find my functions. So I take my function. In order to do this, so say y equals just one thing. This it does factor nice, but I would need to complete the square. Okay, so I'm going to pull out this -3. So if I did try to factor, it would be a -3 minus 1, right? Which we know. But we'll go ahead and factor this. I guess I'm just go a little slower here. So my term here, negative b over 2a squared. Once I pull out the 3, I would be using this interior values. So my b is -4, 2, and a would be 1. So this would be a positive 4 over 2. This is 2 squared. Is like plus and subtract 4, right? I'm basically adding nothing. And then from here, I can pull out my values. Don't forget to include this -3 here, right? So I have +4. This would be a -1. And so when I pull it out of the parentheses, it gets multiplied by this -3, which gives it a +3 value. Okay. Might be a little rusty with putting the squares, so I just want to talk you through that real fast. Then we could complete the square here, right? Finish factoring is y minus 2 squared. So the reason I'm doing this is because now to solve for y is much easier. If I had this in the factor form, I still have two separate y's on one side, and it's very difficult. So now I can solve for x by subtracting 3, uh, dividing by -3 on both sides, okay, and then taking the square root, and then lastly adding 2, right? So now I have a single y, and it gives me those plus and minus values that I need, which is good. And so now I have two different functions. So my area of the washer is the first function the outer function, right, minus the inner function. So remember, pi r squared, this is the radius, the top radius, this is the bottom radius, right? I'm squaring both. So this is the function. This is already a lot more work. Just even completing the square, you could tell is a lot more work than that, right? The only reason you have a lot of math here is because I was doing it very slowly. Okay. So to continue to make a point, this is the area of the washer, and now I need to integrate this across 0 to 3, right? Because now I'm taking a slice in this direction. So I have the top slice and I have the bottom function for the radii. Oops. Okay. So here's my next line. You can see this doesn't even fit. I'm trying to condense things down as best as I can. So I square this perfect square and I square this perfect square. So if I do this, if I square this term, it turns into, oh, it's a difference of squares, I'm sorry. So square this term, sorry, not square this term plus this term, and then this term minus this term without the squares. So I just did the difference of squares, right? A squared minus b squared is a plus b times a minus b. That's all I'm doing, right? I didn't actually do any real math. I just very, very similar to what we did um, for our derivation, way over here, right? R squared, R2 squared minus R1 squared is R2 plus R1, R2 minus R1. So that's where we were. There we go. So it doesn't fit on one line because there's a lot to write. So just the first term plus the other term and multiply that times this term minus this term. So when I start to simplify things down, I can combine like terms, right? So let's see what am I doing here. I have an 8 pi. So it looks like I probably did this on my own. So if I multiply these two things, yeah, it looks like I just did that on my own. I didn't want to go through the work with you guys, so I just kind of did it. So if we FOIL this basically and add everything together, this will be what it condenses down to. Okay, so you can verify this on your own, or if you really, really, really want to, I can add in a supplement where we do that. But you should be able to do this method, factor this out, and then combine down. At this point, it's calculus 2. So, right, yeah, this one times this one, and then this times that times that, and then those two together. So the volume becomes the integral of 8 pi from 0 to 3 of the square root of this deal here, okay, which has no violations because if I plug in 0, I get a negative times a negative, which is positive. So that's okay. Right? Just no negatives inside of the square root. I got to make a u substitution. Negative 1/3 x plus 1 will be my substitution. So basically what I'm doing is I'm factoring out this 3 here, right? If I factor this 3 out, this turns into 1/3 x, and this turns into a 1. And I'm also pulling out a negative, so this turns negative, and that plus it turns to 1. When I differentiate, du is negative 1/3 dx. When I simplify to solve for dx, dx is the same as negative 3 du. Now, when I fill this in, this 8 gets multiplied times the negative 3, so we have that negative 24. This square root of this term here, if you plug it back in and you do the work, you'll see that you get u to the 1/2 power, right? Because basically what's happening is that this whole thing, the 3's canceled. I factored it out. So when I throw it in there, kind of just turns into a u, and this is the square root value. Or you can also think about it as me taking this and distributing it back out. So if I distributed this 1/3, I get a negative 1/3 x, and this turns into a positive 1. It's probably an easier way to think about it than what I said before. Integrating this is now easy. Remember, we're now in u, but my integrands are in x. So this will be 2 u, no, I'm sorry, this will be 3/2. So this will be 2/3. So this will be negative 24 times 2/3 should be negative 16 pi, u to the 3 halves, and evaluate from u is from x is 3 to x is 0. So we resubstitute this value back in, okay? And so now when I plug in 3, I get 0, so I don't have to worry about that. But that would be subtracted from me plugging in 0 here. So that would turn positive, and then I'm subtracting a negative, so that turns positive. So that's 16 pi times 3 to the 3 halves times 1/3. So it's kind of a mess there. Okay, 3 to the 3 halves. This turns into 1, and then we get just 16 pi, right? Which is the exact same thing we had previously with much, much less work. Okay, so again, that's just me making a point where one method is always easier than the other. Because we skipped a whole bunch of steps to go from here to here. I'm leaving that to you, the viewer, to flex your algebra skills and go ahead and verify that. But our volume, our areas came out the same. The volumes came out the same. Okay. All right. I hope that was helpful. I will see you guys on the next video.